Hello everyone, I am making this recording in order to help you review the Unit 2 Portfolio number 2, which is a Unit 2 review exercise. So question number 1, if angle 1 and angle 2 are supplementary angles with the measurement of angle 1 equaling 10x plus 5 and the measurement of angle 2 equaling 6x minus 1, find the measurement of both angles. So essentially with this, Um, you have to first interpret what the word supplementary means, which means you have two angles that add up to be 180 degrees, and you're going to be using that fact to write an equation. Therefore, these two angles, when they take their measurements and add them together, they should total 180 degrees. Well, since their measurements are represented by 10x plus 5 and 6x minus 1 respectively, I'm going to make the sum of those two things equal to 180 degrees. Now, I've seen students, they'll always say they equal to 180 degrees, or they'll set two things equal to each other. You have to use the concept that they're talking about. If I had said that angle 1 and angle 2 are congruent, that'd be a different story. If I said they were complementary, and I would take them, add them together, and say that equal 90. So you have to use what's in the problem in order to, set up your equation. But for this one here, I took 10x plus 5 plus 6x minus 1 to equal 180. And then as you follow along, next I combine some like terms. So the 10x plus the 6x became 16x. The 5 and the minus 1 became a positive 4. I then subtracted 4 from both sides. As we move through the rest of this first semester, you're going to be, and oftentimes being asked to justify your steps as you go along. So I would probably say at this point, when I go from step 2 to when I go to step 3, I'd probably say that's simplification. Just going to abbreviate. And then I would probably say for, give you a second here, for, line 2, I'd probably say that was because of the subtraction property of equality. This I would have probably said was from substitution. And definition of supplementary. I'm just going to put the whole thing in. And then lastly, when I divide both sides by 16, that's by the division property of equality. So you're doing some of the algebra, but now they're going to be expecting you to slowly but surely start describing the reasons for why you're doing what you're doing. Number 2, same thing. It says, given that GI bisects the angle DGH such that DGI equals 5x and IGH equals 3x plus 10, find the measurement of DGH. So basically DGI and IGH would be the two angles that are formed from angle DGH being bisected by GI. But I also have to keep in mind what bisect means. It just doesn't mean cutting the angle into two parts. It means cutting the angle into two equal parts. So when I look at this, these two angles, DGI and IGH, DGH is the original angle. These two angles here should be equal in measurement to each other. So basically, they're equal in measurement, or I could say that DGH is twice the measurement of one of those two angles together. Since I do know what those two smaller angles are, what I do is I set them equal to each other, because that's what bisect means. Those two angles that are formed from splitting the bigger angle should be the same measurement. So 5x would equal 3x plus 10 by the definition of bisect and through substitution. I then subtract 3x from both sides. And again, that'd be the subtraction property of equality. So we're going to get more into this as we move into Unit 3 as far as naming our steps. And then I divide both sides by 2 to get x equals 5, and I would probably say that's by the division property of equality. But as I said, we haven't gotten into the properties a whole lot yet. We will. But just to give you a heads up about what's coming along in the future as well. Since I now know that x equals 5, x is not what we were looking for. We were looking for the measurement of angle DGH. So I could either realize that by putting 5 back into one of these two, I'd get 25, and 25 together would be 50, or I could kind of just realize, well, that's 2 times the measurement of one of these two. I find the measurement of angle DGI, which is 25 degrees, and since DGH has to be twice that, it's 50. So there's different ways to go about figuring it out, but you should show how it is you did figure it out. That's the important part about these portfolios as we review them, is knowing the steps needed to get to the answer. For number 3, midpoint problem. This is an issue that a lot of students have. I mean, if it just says find the midpoint, it's usually a pretty simple problem. I mean, it's just, you take the average of the x coordinates, you take the average of the y coordinates, it's all set. Here, though, they're giving us the midpoint, they're giving us an endpoint, and they want us to find where the other endpoint is. And that's different. A lot of students make mistakes on this test because they will just take the 2 coordinates they're given, use the midpoint formula, and call it quits. Meanwhile, they're not asking you to find a midpoint, they're asking you to find another endpoint given that you have a midpoint. So for this question here, I kind of keep in mind, and I think the easiest way is to kind of imagine a graph. So here I'm not really graphing everything super accurately. But I have the endpoint u at 9, -5, and I have the midpoint 5, -2. And I notice that as I move from u to the midpoint of uv, I'm moving up 3 units and to the left 4 units, which means if I go from the midpoint to the other endpoint v, I should be moving another 3 units up and another 4 units to the left. And so with that and some basic subtraction or counting, I could figure out that v would have to be at 1, 1 for this to happen. And that's where the other endpoint is. So the calculations are not that extreme. I mean, you can also use the midpoint formula. You should realize that, when you're doing your x1 plus x2 over 2, you don't know what one of those x's are, but you do know what the final result should be because you know the midpoint. So I could say x1 plus 5 all over 2 should equal, no, let's take that back, x1 plus 9 all over 2 should equal 5, and that will help. That can help you figure out what the x coordinate is of that point, and then do the same thing with the y's. Anytime they ask you for the distance between 2 points, you can sometimes get away with an easy one, but if you notice that if none of the x coordinates are both different and the y coordinates are both different, you don't have a horizontal or a vertical line. Those are easy because you could just usually subtract the 2 coordinates that aren't the same, and then that's your distance. That means that these 2 are diagonally oriented from each other. So, and there's no easy way to find the distance, just by even if I graph it by counting it. So what I have to do is I have to use what they call the distance formula. And you do have it on your formula sheet, so make sure you don't get it wrong because you're not using the formula sheet. But the distance formula essentially says, okay, I'm going to take my 2 x coordinates, here's x1 and x2, I'm going to subtract them, then square them, and I'm going to take my 2 y coordinates and subtract them and square those. I'm going to take those results and add them together, and then I'm going to square root that. So when I take -1 minus 6, I get -7. When I do 5 minus 2, I get 3. -7 squared is 49. 3 squared is 9. I get the square root of 58. And since they're telling you to round here rather than write an exact answer, you just do the square root of 58 on your calculator, round to the nearest tenth, you get about 7.6. So they're about 7.6 units apart. Using the figure to the right. Some students have issues with the various ways we name things because there's multiple ways of naming lines, planes, what have you. They do ask for what is another name for plane P. Now notice, this is how I know this is the name of the plane because it doesn't have a dot next to it. If it has a dot next to it, it means it's a point. Okay, so I'm not going to say it's point P, and I don't want to put that in the name. I don't want to say Well, if I use these 3 points, because usually we name a plane, if we don't have a single letter name for it, by simply naming it and putting that letter in one of the corners, um, then I have to use three non-collinear points that are on that plane to define it. So some other names for plane P, based on this figure, would be VRQ, because you can see those three are not linear. I guess say VRS, because I can see those three are not collinear. Line VQ, I say VQS. There's different things I can name. Some of the letters could be rearranged a bit, but I could say RSV, that kind of stuff. So there's different names I could give it, but as long as you're using three non-collinear points to name it, that is sufficient. Opposite rays have to together form a line. They have to have the same endpoint. So if I say one has an endpoint of Q, the other one has to have an endpoint of Q. And I can see that QR and QS do form a straight line. So those are opposite rays. Whereas if I say like, QR and QT, that's not a straight line. You can clearly see there's a bend here. So, they may have the same endpoint, but they're not opposite rays. Now, QT and QN form line M, so you have that. Plane TQS, which is not seen in the figure, and plane P would intersect at. Now, the one thing you have to keep remembering, and a lot of students mess this up. If you have two planes that intersect each other, they form a line. And since they're saying, okay, T, Q, and S, I mean, here's those 3 points. So you have to imagine that the plane that is alongside of them, is like right here. So here's the plane. It's intersecting them. And I can see that, basically that forms a crease, and that crease is that line. Now, when we draw planes, we can't draw infinite things. We draw these parallelograms to represent them. We do recognize that all of these planes are going on forever in each direction. This one down here as well. It's coming out this way. That one's going this way and this way for the forever and ever. That's why it's a line. It looks like it will be a segment in our picture, but I have to remember that these are infinite, and therefore that crease would be infinite, and that makes it a line. So I could call. I mean, there's different names I could give that line. I call it could be line L, as we see it's labeled here. If I get rid of some of those markings, line L. I could say, I call it QS. As long as I'm naming 2 points that are on the line, it doesn't matter which order they're in because it's a line, because it has no endpoints. I'm good. As far as the number line goes, when they give you a number line, it's not that hard to follow. I mean, you could use formulas for some of these things, or you could just count. I mean, since what 2 points lie 3 units from E? Well, here's E right here. And all I really do is just count, it's like, okay, well, 1, 2, 3, I'm at H if I go to the right, and 1, 2, 3, I'm at B if I go to the left. So that's not too bad. I don't know if all the answers come in at once or... So H and B would be those 2 points. Name 2 line segments congruent to AG. Okay, well, if I go from A to G, that is 6 units in length. So I want 2 segments that have the same length. Well, I don't have a whole lot of options here. If I start like at F and go this way, I don't have any more points beyond I. So if I say, okay, well, if I move 6 this way, starting at B, I have like 1, 2, 3, 4, 5, 6. I would stop at H. So I could say, well, BH would be 1. And I could say the same thing for, if I start at C and move 6 units, I could say, well, CI would be another one. And since they're segments, again, it doesn't matter which order I name them, but I have to name them based off of its endpoints. If I name a segment, I can't say like segment BH is the same as segment BG. They're not, because BG would only be 5 units long. Whereas if I was saying, okay, I mean, if I was naming this entire line, I could use any one of these and any two of these points to name it. I could call it line AB. I could call it line AF because that line is infinite. Whereas on a segment, you know, the end, what I name it is telling me where it ends, the two places where it comes to an end. And what is the midpoint of HB? You know, we can see again, here's HB. As we said before, it's 1, 2, 3, 4, 5, 6 units in length. So if I go halfway, which would be 3, 3 here, 3 here, I'm at E again. So if you have a picture in front of you, it does make it a little easier, but some of those formulas are kind of there to keep you from having to do that. Yeah, for number 9, I also say if you state GA, you're technically right, but it's kind of it's not the intention of a problem like that, you know. So because yeah, AG and GA would be the exact same segment, so they would have the same length and be congruent. So get back to what the midpoint of HB is. It is point E, as I showed up there. Oftentimes when they describe things to you, it's a good idea to draw pictures along with it. I mean, yeah, but since you're talking about you have length and width for a rectangle, I mean that's those are two different sides of the triangles, or like those are the sides that intersect, not the opposite sides, which would be the same. But I do want to know what its perimeter is. They tell you the perimeter is 18, the length is 6. What's its width? Well, I have to keep in mind that we do have a formula for perimeter, because if you think of it on a rectangle, you know I have a length, a width, and a width. So I have 2 lengths and 2 widths being added together to get that perimeter. They do tell me that the perimeter is 18, so I replace P with 18. And they do tell me the length is 6, so I replace L with 6. So here's where some of your algebra skills can come in handy. So 18 equals 2 times 6 plus 2W. I come over here. 18 equals 12 plus 2W. I then subtract 12 from both sides. Or I say, subtract 12 from both sides to get 2W equals 6. And I divide both sides by 2 to figure out that the width is 3 feet. A triangle has a base of 19 inches and a height of 11 inches. What is the area? Now that one's pretty easy because we know that the area of a triangle is 1/2 the base times the height. And since they're giving us the two things that are in that formula, I really don't have to draw it. I just have to make sure I plug them in the right spot. So I'm going to do 1/2 19 times 11, and that ends up being about 104.5 square inches. What is the circumference and area of a circle that has a diameter of 9 centimeters? Round your answer is the nearest hundredths. For circumference, it's pretty easy because, I mean, circumference has two formulas. You either have 2 pi times the radius, or you have pi times the diameter. And since we know what the diameter is, you know, that's pretty easy. I could just say, well, that's going to be 9 pi centimeters, or I could even, since it says round the nearest hundredth, when I evaluate 9 pi, it's about 28.3. For the area of a circle, I only have one formula, pi r squared, and I have to kind of say, well, you know, I don't have a radius, I have a diameter. But if you realize a radius is half of a diameter, that's all you really need to be concerned about. So I take half of that 9 and then square it, which gives me pi times 4.5 squared, which is 20.25 pi square centimeters. And don't be surprised if you see answers like this represented in your textbook from time to time on tests and quizzes and things like that. You may have already seen some. But since here they say round your answer to the nearest hundredth, that means that they maybe want you to evaluate it a bit further and you carry out the calculation. And 20.25 pi is about 63.6. In this case, it's going to be square centimeters. So you're told you have a trapezoid. It's made up of STUV. Line segment BC bisects angle SCT. And for our purposes, that kind of means that, you know, I should already know that these two angles would be congruent to each other, because that's what bisect means. If we want to use that information in this figure to help us find the measurements of these. So we do know that the measurement of angle TCU, give me a second here. I'm getting a message showing up on my screen here. Give me 1 second. There we go. There we go. So the thing is, I mean, when I look at, you know, this angle here, which is made up of two different parts, and I have this angle here, so make it a nice dark one. I do see that they form essentially a straight line. So I know that these three angles, you know, UCT, TCB, and SCB would all total 180. I also know that angle VCU would total 180 along with angle TCU as well. So, you know, I can see which ones are supplementary because I can see which ones are linear pairs. So that's kind of the way I approach this problem. Is like I try to take the information I have, see if I have any linear pairs, and try to go from there. I also have vertical angles. So like when I ask what SCV is, now we haven't formalized this. We have talked about vertical angles, but we're going to have eventually proofs and talk about that vertical angles are congruent to each other. So I do know that the measurement of angle SCV is going to be 66 degrees. When I look at the measurement of, you know, as far as finding these other angles, UCV, BCV, I took this fact that 66 plus angle SCB and BCT should total 180, but I also know that these two, as I said before, are the same measurement. So it's like me having two of one of them. So what I did is I said, okay, well, since SCB is just one of those angles, I'm going to have 66 plus 2 times that angle, which would equal 180, which means 2 times that angle would be 114 degrees, which means SCB would be 57. I do know that this was 66, as I said before, because of the vertical angle theorem. And this is 114 because if I go from here all the way through here and end up back here again, that's 360 degrees. That's a circle. So, and also I could say that because these two angles total 114 up here, these two, and kind of looks like Mickey Mouse. And the angle, you know, that angle SCT is a vertical angle with VCU or UCV, whichever way you want to read it. Therefore, they should be congruent to each other. So you can see here, I mark up the figure before I worry about doing anything else. And now with all these little measurements, I can now put answers in for 14, 15, and 16. 14 is 66 degrees. UCV is 114 degrees, and BCV, which would basically be this angle here and this angle here added together, and those angles do total 123 degrees. The isometric and orthographic drawings, there are some questions that are on the test that are dealing with this. Usually they do give you a picture of an isometric drawing, or they give you one of these pictures, which is almost in itself kind of what an isometric drawing is going to look like. And they want you to interpret what the orthopedic drawing would look like from a certain vantage point, or they may give you several orthographic drawings and want you to pick out the three-dimensional figure that it's showing. So as I said, this doesn't look much different, you know, as this. And it just takes some practice, like knowing how to use the dots and to show the slants and the depths and so. But as far as the orthographic drawings, remember, when you do them, you're supposed to show front, top, and typically the right-hand side. Those are the three views you use most often. You do have to show three views, usually. So if they do ask for an orthographic drawing, you must show three different views. That's one answer. So for this one here, I can see the front, you know, here's facing front, facing front, facing front, facing front, facing front. So that's why it looks like that. When I see the right-hand side, you know, here's R, 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 and R. And then T, here's, of course, the tops. And that's how I get those pictures that you see down there. You just have to see, okay, well, I'm only seeing that. I'm seeing like a two-dimensional view because I'm like directly over it or directly on its right hand side or standing right in front of it. This one here, drawing a net of the following polyhedron. Now I can see here what I have is I have a trapezoid here, and in back I have a rectangle here. It looks like a parallelogram because it's kind of supposed to be slanted, and looks like a rectangle, maybe even close to being a square. And down here I have a rectangle, which is bigger than its top counterpart. So when I imagine that being unfolded, it doesn't matter what I have connected, but I kind of like use this as my main focus point, the top. And I call that number 1. Okay. So, so I folded this out this way, folded this out that way, folded the back, this way, folded the front out this way, and I left the bottom attached to down here. But it's kind of a bit, more on the difficult side to kind of visualize this for some people. But again, this doesn't make up a whole much of the test, and it's something we're not going to be looking at again until we start discussing more three-dimensional figures towards the end of the course. So if you're having trouble understanding this, it may cost you some points on the test, but not enough to make you fail it. And it's certainly something we're not going to be visiting very frequently for quite some time. So. And that's all I have for this review of the Unit 2 portfolio. If you have any questions, please feel free to contact me. But until I have a chance to talk to you on the phone or I see you in a live lesson, I will see you around. Have a good day.